continue. Alright, let me explain more. If I have a high frequency transmission line, it has a dense L, and also the important notations are beta and Z0. Okay, I have a transmission line. Okay. The voltage equation on this transmission line. Okay, write down B. Okay, and also current. We just think about the voltage. Can I connect the transmission line to something? ZL? Yes, we can connect to ZL, as I just said. What is ZL? ZL means I don't know what it is, but the only thing I know is the voltage over total voltage over the total current at this point is ZL, the impedance. This is the only thing I know, okay? Can I replace ZL to other transmission line? Can I do that? Yeah, of course, I can do that physically. I just connect it, right? Or can I, let's go back to ZL. Can I say Z equals to 1 is in the middle of my transmission line? Can I do that? And so here it is Z equals to half L, and for here it is Z equals to minus L over 2. Can I do that? Of course, I just change something. Okay. Can I set, if I do that, can I set this is a new ZL, okay, I call it ZL2. Can I say that? Can I make the load box larger? Or I said, because I set up Z equals to 0 at here. So my transmission line, it is now part of load. Can I say that? Yes. Okay, I can do that. It depends on how I try to define. For this example, let me go back to the original one. I focus the question on some unknown load connect to my transmission line. I focus on this question. I define my reflection coefficient to V minus Z0 minus over Z0 plus is because when Z equals to 0, this term, the forwarding term is V0 plus, and the reverse term is V0 minus. At Z equals to 0, this is according to the definition. So I have this result. But in the real world, in general, it is not always true. Okay? It's not always true. The thing I want to tell you is I want to make this equation more general. Actually, this, as I said, I can write down 0, z equals to 0. Or I can just get rid of z equals. This is a function of z. Gamma z equals to v0 minus over z0 plus. And gamma z equals to the v0 minus multiply exponential plus j beta, if this is a lossless case, over down, it's j 2j beta L equals to gamma z exponential 2j beta z. You guys understand this equation? Gamma is supposed to be a function of position, which is the reversing voltage over the forwarding voltage. Okay, it is lucky at z equals to 0. This term is 1. So this part is gamma 0. Okay. So, what did you observe is gamma, it is a function of position, and the gamma has direction. Because I told you this one is reversed, this one is forwarding. So I'm telling you this one is positive, this one is negative, right? For this one, I tell you, if I can write down this one, equals to, okay, this turn over this term, right? But it is possible that we can read this term, so you will change the position. Okay, so it's possible that in your world this guy is a good man, and then that one is a bad man. But in other words, it's changed. That one is a bad man, and this one is a good man. It depends on how you read the direction. Okay. Gamma, it is a function of position, and you should tell us which direction you are looking at. If you do that this way, you do that this way. But if you at this position and then you do this direction, then you make opposite. Okay? Okay? I think it's more than on my slide, but it is important. Gamma, it is also a function of position, and it has a direction. It depends on which way you look at. Okay. So let's go to next part. Okay, one more thing. Go back to our original transmission line. at this position, I told you that the impedance, okay, let's define Z input impedance, equals to the total voltage over the total current, and at this position, Z equals to 0. At this position, right? And because of the load here, you don't see other transmission line equals to 0 here. This is what happened. We already did here. Okay, the voltage and the current at that point is here. But don't you guys curious about, so your impedance at this point is ZL. Doesn't matter what I connected. Don't you guys curious about that? No matter what I put here, your impedance is 0. Because the definition is too broad, it's not accurate. Your impedance, the same as this gamma, has direction. Your impedance read to this direction is this one. Okay? Your impedance go this way is this one. But your impedance read this direction is another impedance. Okay? They are different. So the same as the reflection coefficient, your impedance is a function of position, and also it has a direction. Z here, it is different. It depends on something else here. But ZL is something right here. Okay? Our next job, our next objective is to derive, because Z input impedance here is at Z equals to 0, right? We are trying to know what's the difference if I have the transmission line. What is your new Z in at Z? At another end of the transmission line, what is your total impedance? The impedance will change because we have transmission line, we have load. So the result of your impedance Z in, it is impedance equation equals to the total voltage. Let me just copy it. Minus J beta L plus V0 minus plus J beta L, and I get rid of V gamma V0 plus. Okay, and for this term it is Z0 V0 plus exponential minus J beta Z. And gamma, just copy that term. It's minus Z0 gamma V0 plus exponential plus J
Okay? I just put the number there to here. I try to find out the answer. And this one equals to, I multiply Z0, and I will take V0 plus away, and I will get minus J beta Z minus gamma exponential plus J beta Z and exponential minus J beta Z plus gamma exponential Z beta. Okay? Can you follow? Okay, I multiply Z0 for the numerator and the denominator, right? And they are the same. And this one equals to, there are more details. Don't know how much can I do, right? Multiply. And I remember I should take, first of all, I will use gamma equals to ZL minus Z0 and ZL plus Z0 in. I need to put them in here, and I will simplify the beta L to theta. Is a phase, the electrical phase, the phase. Okay, so let's do that. Exponential J theta plus this one is ZL minus Z0, ZL plus Z0 exponential plus J theta. Exponential J theta plus I multiply ZL plus Z0. So Z0 come okay. I think it's very close to what I want to. Show you the thing I derived. Okay. So I put that in, and I changed the, I didn't change the information j theta to cosine the sine here. Okay, if I put a cosine and sine here, and I will get divide by cosine theta, and will obtain 1 plus j tangent theta for Newton, and for others I will get a 1 and the tangent instead of cosine and sine. And this one comes from the Euler exchange, right? The Euler, right? Explanation j theta is the cosine theta plus j sine theta. I transfer that, and this is the cosine theta minus j sine theta. Yeah, I didn't do that. But after I do that, and I put a gamma here, you will have, yeah, it's a little bit ugly. Just put everything there, and I think the most complex thing is you need to find same stuff to combine the same stuff to delete the same stuff, and you will find. And you can see my website if you try to derive it. And the final result is beautiful. It's much simpler. It is z0 multiply zl plus j tangent jz0 tangent theta over zl plus jzl tangent theta. And the theta is beta L. Okay? And don't worry about it. You can open book, right? For your exam, you can open book. Okay. I just derived it for fun. Because in your textbook, you just see this one and at the end, right? I just write down how to derive it. Okay. So you use something. First, you need to change. You put gamma equals to ZL minus Z0 over 0 plus 0. You need to put this one, and also you need to put this one instead of, you use cosine theta plus j sine theta instead of this one, and then minus sine theta for the exponential to the minus j theta. It's not hard, but it is very detailed, trivial. Okay? And the last term is you need to cancel everything, and that's something. Okay? Okay, so you guys can understand. So what can we do for this one? We try to calculate the input impedance at any position. If I have a load, ZL, I have a transmission line. The transmission line has a characteristic impedance Z0. And the transmission line, I have a beta and I have a length. I will know what is your new input impedance according to these parameters. I connect this transmission line to Z0, and that will change to new impedance. Okay? But the most important thing is you know how to use this equation to find out if there is a transmission line connect to a load. Okay? So this is, we call this transmission line impedance equation, and it is very important. This is one of very important equation. You need to mark it. You have a question on it, and the most important thing is your Smith chart is talking about that. Okay. When I tell you about the reflection coefficient, the impedance, the input impedance, I'm telling you the theory of Smith chart. This is one of the very big issue in chapter 2, Smith chart. Okay, if you try to find a job related to RF engineering, they ask you about Smith chart. This is very typical question. And I'm telling about the input impedance and the input reflection coefficient. Or and maybe you said it's a impedance at any position or reflection coefficient at any position. It is Smith chart. It is related to Smith chart. Okay? Okay. So from at the beginning, we are trying to derive impedance equation first. And this is actually what I'm trying to do in a beautiful slide. Because I realize that if I write down slowly with you, you can understand more. I can show you directly from the PowerPoint and then nobody can learn because it's too fast, right? But after I show you on the whiteboard, I write down it step by step and come back to see this one on your whiteboard. You know the total voltage you can write down like this form, and you have a transmission line with the length L, characteristic impedance Z0 and beta. You have a voltage and current on it connect to some load, right? You define your L equals to minus Z, because L is physical length and Z is the position. So here is a minus Z. You can transfer your voltage, the function of voltage to L, right? L is the position. Because it is a minus, so you change the negative side for this part. For the J beta L, you transfer from minus to positive, transfer to positive to negative because of L equals to minus Z. And this is a new voltage equation, depends on the length. Okay? So, actually totally the same thing as what I did on the whiteboard. You put everything, all the voltage and all the current is a function of L to describe your Z in. And then you just put everything in, do the organization, you will find out the result, the set result. Okay, and for this equation, it depends on the L, beta L. It's not Z, because Z equals to minus L. So important. And if you are not satisfied with my derivation, you can also see 2.44, the equation 2.44. Is there any derivation on it? Yeah? You see a derivation on it? Okay. So you know the reflection coefficient, you know the impedance on any position of your transmission line. You want to continue? Or maybe I try to slow down, okay? I give you more things. And let me try to, maybe you can do some preview. But next week, we are talking about what is ZL. I will connect exactly something for the ZL. There are 4 possibilities. What we can connect. We can connect ZL to open, short, low, and maybe a match. We can connect something for the ZL, and we will use the Z equation to see what happens if your ZL is something special. Okay? I think that's it for today, okay? Okay, I don't want to pour everything on you, then you cannot digest. Yeah, spatial case. So next week we are talking about something. Okay, if you don't understand the details, try to ask your classmate or me to understand what happened. Do you guys need more questions, please? To help you to understand. Okay, let me, after I revise your quiz, then I know how much you understand. Yeah, you don't act like you think you understand, but you cannot get the right answer. I don't think that's not good thing, especially you forget a unit. Don't forget anything. Don't forget anything. Okay. So next week we will change ZL to short, open, matching. Matching means connect to Z0 and connect to half wave. And okay, if this length is half wave and this wave is quarter wave transmission. Okay, this is for next week because they are related. I don't want to cut it in the center. Okay, 20 or 10 minutes is not enough to explain everything. Okay? Alright, so we finish.